That's all good.
Thank you so much, everyone. Thank you as well, Dr. Hussein. So to kick things right off, please note that you will be able to minimize the notifications that might come through whilst you are within this webinar. You can turn them off should you wish to do so, and then you can also turn them on once the presentation has concluded. You can make use of the chat box in order to send your questions. If there are questions that are relating to today's topic, then you can go ahead and leave them in the chat box. I'll be sure to to compile them and then give them to Dr. Hussein to answer for our post-webinar questions or post-webinar question session. But any questions that are relating to the Engineering Institute of Technology, I will be able to answer them for you during the course of the webinar. So some common questions for you guys. Please note you'll receive a copy of these slides as well as the recording. They'll be sent to your mailboxes by the EIT marketing team. Within a day or two, they will be sent to the email addresses that you used to register for this webinar, and they will come through within 24 hours. You should have them. Regarding the certificate of attendance, you will also have the opportunity to request for the certificate of attendance. Kindly note, I will only be providing the link at the end of the webinar. I'll provide you with the link as well as leave the QR code up on the screen so that you guys are able to request for your certificates of attendance. Please make sure that you input your names correctly the way you would want them to appear on the certificate of attendance so that you guys are able to get those certificates, and you can share them, of course, on your social media platforms and tag us if you can. If you guys are new here, let me tell you a little bit more about the Engineering Institute of Technology. We are an engineering specialist. We specialize in engineering programs. We have a professional certificate that is about a 3-month short course, all the way to the highest academic level you can get to, which is a doctorate level. We have a Doctor of Engineering program that we offer at the institution. We are also a world-class Australian accredited education provider, and some of our programs are actually internationally recognized under the Dublin Accord, the Sydney Accord, as well as the Washington Accord. We also have industry experienced lecturers, meaning that our lecturers have actually worked in the field, and now they are imparting the knowledge that they've gained in the field into the studies that they conduct at EIT. And then we are also one of the institutions that offer a blended learning module, meaning we have courses that run on campus as well as online. The nice part is that all our programs can be done 100% online, regardless of where you are. As long as you have a stable internet connection and a laptop, you'll be able to study with us. And then we do have programs that run on campus. Those would be our HE courses, higher educational programs, the bachelor's, master's, as well as the Doctor of Engineering. And you can study on campus over in Australia in one of our 3 campuses, either in Melbourne, Perth, or in Brisbane. And then these are the reasons why students choose to study with us at EIT. However, so as to not waste any time, you guys are going to receive these slides. You'll be able to see all of this information. As I did mention, that it will be sent to your mailboxes. Now, today's topic is one that is of interest. It is called the Introduction to Battery Energy System Storage, or rather energy storage systems and their support systems. This is going to be by Dr. Hussein Tafi. He is an EIT lecturer and he'll be taking over. If you guys have any questions, as I've mentioned, please leave them in the chat box. I'll be sure to collate any technical questions to the lecturer, and then any questions that are regarding EIT, I will answer in the chat box. Thank you so much for your time. I will see you at the end of the presentation, and I will leave you in the capable hands of Dr. Tafi. Thank you so much, guys. Dr. Hussein, you can go ahead and take control of the slides.
Thank you very much. Thanks everyone for joining this session. Take control. Okay. This is me. I'm currently a lecturer and course coordinator at EIT. I have been with EIT the last 3 years. Previously, I was a research fellow at the University of Western Australia, also at the University of New South Wales. I got my PhD from Singapore, NTU, Nanyang Technological University, and my main major is on power electronics, grid integration of renewables, and energy storage systems. And that's what we are going to discuss, some of the basic elements of energy storage systems and how they can support the power system under the high penetration of renewable resources. So there are few points that I will be covering. Maybe I just go back to this agenda. Firstly, we start about high penetration of renewables and their challenges. Everyone is aware of the importances and advantages of renewables, but something that is not being discussed many times is challenges that we get with high penetration, and that's what I will be discussing and starting this presentation with. We'll talk about energy storage technologies, different technologies that we have, and only one of them is battery technologies. And from there, we'll go a bit more specific to different types of battery energy storage technologies. We'll continue with the power converters that connect the battery storage technologies or systems to the grid. And then we'll talk how can these battery energy storage systems provide power system support. We'll quickly also touch base on some of the safety standards that are important in battery systems. And we'll conclude the session with some emerging technologies that exist in battery systems and their importances. And okay, let's start with the first part in which we are going to talk about the high penetration of renewables and the challenges. Everyone is aware that nowadays renewable systems, solar systems, wind are increasingly being installed in the power system in almost all the countries around the world. This is happening, so I don't need to repeat that. Of course, they have many advantages, but let's look at some of the challenges. One of the challenges, or one of the big challenges of renewable resources is their dependence, or sorry, independence to environmental conditions. For example, a photovoltaic system, the output power of a photovoltaic system is dependent on the irradiance. For example, if we have a sunny day like what we have in this blue curve, from the sunrise to the middle of the day, the output power from our solar panel would increase and then would decrease the rest of the day. However, the same solar panel on a rainy day or a cloudy day will have a lot of power fluctuations into the grid. Now, this is the biggest or one of the important challenges that we have because originally or conventionally we had power generators uh, in which we were able to control their output power. We had the control of their output power. But suddenly we are moving to a system or to renewable system in which their output power is dependent on the environment. And that's one of the big challenges, right? So we have the same story for wind power systems as well, in which the output power of the wind system depends on the speed of the wind speed of the wind system. Sorry, speed of the wind. So this is one of the best challenges that we have. If we continue, we see another big challenge as well, in which there is a lack of inertia. So since the inertia may not be very familiar for everyone, I need to give a little of explanation here. Conventionally, we have synchronous generators or in general generators that are producing electricity. I mean, their main input source could be hydropower, could be steam-based power plant, could be gas power plant, etc. But we had synchronous generators or in general generators to convert different types of energy or different types of power to an electrical power, right? So one of the important features of generators is a big rotor or big mass of rotor inertia that is embedded in the generator to generate electricity. Having such a high amount of inertia in the rotor helps a lot on the power system stability. And we have And when we have this information, we have this feature in that any difference between the electrical power and the mechanical power that is fed into the generator is compensated by the rotor. And that provides a big inertia. This inertia helps to stabilize the power system, and there are some many mathematical equations to solve to demonstrate that, which we are not going into the details here. Now, what we are doing, we are removing generators, or we are reducing the installation of the generators because we want to install photovoltaic power plants, because we want to install, let's say, wind power plants. Now, in in addition to the power fluctuation problem that we mentioned in the first slide, now we have another issue, which is called lack of inertia. We are removing the inertia of generators, or we are reducing the available inertia in the system, which is the main reason for stability of the system. Now,
Dr. Tafi?
yes,
My apologies. Can I just reshare the slides again? I have a few people saying they cannot see the slide. This might be a Teams related issue. However, I'm
sure.
just going to try and share from my end of the screen. We are on slide 13 of 57. So I'm just going to share it onto my desktop and see if that will suffice for the users today. Just a moment, ladies and gentlemen. I really do
Sure.
apologize. Okay, I've shared the slides on my screen right now. Let me take you to slide 13, Dr. Hussein, and then you can just as well continue with your presentation. If you guys can please tell me if you're able to see, okay, there we go. I really am happy that you guys are able to see the screen. Could you please see if you're able to take control, Dr. Taffy?
Yes. Request.
Yes, you can go ahead, sir. Let me just,
So now, can you put it in the full screen mode, please?
okay, just a moment, please. Are you able to see the screen properly now?
Yeah, we are seeing the screen, but not in the full screen mode yet.
Is that good?
But not in the full screen mode yet. Oh, now it's better.
Okay.
Let me see, pen. Okay, now it's good. Okay, good. Can I continue?
You may continue. Thank you so much, Dr. Taffy.
No worries, that's all good. Sure. So we were talking about the inertia and the feature that inertia provides for a power system. Now, with removing the inertia of the generators, or with reducing the installation of generators, we are removing or reducing an element which was an important element to stability for the stability of the power system, and that is inertia. Now, the effects would be larger frequency variations at what we can see in the second figure on the right. You can see with high penetration of renewables, the frequency variations that can happen after any change of the load, any differentiation in the load compared to the mechanical power would be higher. And this could lead to stability issues in the power system. This could lead to the blackout in the power system. And this is another issue that we have in a power system with high penetration of renewable resources. In addition to these two big challenges, there are other challenges. And now one of them is the lack of visibility. If you think of the conventional power plants, they were fully governed with the power system operator. This means power system operator, through the SCADA system or through any type of control and communication they have, they could regulate the power, they could regulate the operation mode of those synchronous generators or centralized power generators. However, nowadays, with distributed generation from photovoltaic inverters that are installed in almost all the houses, especially in Australia, we are having a lack of visibility because not all of these PV inverters or wind inverters would be talking or would be communicating with the central system. Now, that lack of visibility makes new uncertainties in the power system since because we cannot regulate the power directly, we cannot see exactly the operation mode of each of these inverters, and there are other issues related to this lack of visibility. And of course, with the lack of visibility, we also are losing the lack of central control, right? So now you can see now if we put all these few issues or challenges together, we can see that high integration of renewables in the power system has many challenges, has many issues. In one part is not good, in one part is good. In one part is the part which is not good is the challenges. It may make the power system unstable. It may we may not be able to integrate 100% 100% the renewable based power system and so on, right? So there are different solutions. This was a good, this was a negative part of it. A good part of it is this is a new challenge in the power system, and of course that means that the power system requires extra work, which is good for us like electrical engineers, right? That's why we are talking here. So one of the solutions, just one of the solutions, are energy storage technologies. Again, I repeat, this is energy storage technologies are one of the solutions to integrate high penetration of renewables. There are other solutions which we can implement in the power system to reduce those challenges. But here our focus is energy storage systems. Once we talk about energy storage system, most of us may only think of battery system as a type of energy storage system. However, in reality, power systems are integrating many different types of energy storage systems, being mechanical, being thermal, being electrical, chemical, or electrochemical. You can see the batteries are only part of this whole classification that are classified under the electrochemical. But in addition to that, we have chemicals similar to what we have for fuel cells that are converting the electricity to hydrogen. That's one way. This is becoming also popular and becoming an interesting technology. We also have supercapacitors or supermagnetic systems in which they store electricity as electrical. We also have mechanical ones. So I quickly discuss some of them so that we have a better idea of different types of energy storage systems, and then we go a bit more deep into the electrochemical or battery types of battery types. Before I move from this slide, I would like you to also look at the various types of battery systems that we have. Again, we may think always uh, lithium ion batteries are the only solutions, but that's not the case. We have different types. We have like lead acid batteries that are conventionally being used um, the conventional being used in as a starter of conventional machines or sorry cars. We have lithium ion batteries, we have sodium sulfur batteries. Nowadays we have new types of batteries that are flow batteries, such as vanadium redox batteries or ZNBR battery, right? So again, there are different types of battery systems that exist. Now, coming to a quick overview of different types of energy storage technologies so that we get familiar with them. One of them, one of the famous ones, or that is being used a lot also, is flywheel. Flywheel, as shown here, it is a mechanical energy storage system similar to the operation of a synchronous generator. However, in a flywheel system, we are not generating electricity, or we are not converting electricity from mechanical energy. What we do here, we have a big mass of rotor which has a big inertia, and then we run this as a motor in which it starts and increases the speed of the rotation of the rotor, and by that high speed rotation of the rotor, we have a mechanical stored energy in in the rotor, right? So now this is a source of energy. This is a way that energy is stored. Now, whenever we need electricity from the grid because we have lack of mechanical power in the grid, or the frequency is decreasing, etc., this system, which now has stored energy in the rotor, can convert the mechanical energy into electricity, and it can run like a generator. So in simple words, when I have excess energy from the grid, my flywheel operates like a motor, and by operating like a motor, it keeps increasing the speed of the flywheel rotor, and that means it's saving, or it's storing the energy as a kind of mechanical energy. On the other side, when we have lack of electricity on the grid, in which we can inject our power or store power to the grid, the flywheel works such similar to a to a generator, and it converts its stored energy into electrical energy for the grid. That's one type. The other type of mechanical energy is the pumped hydro storage energy storage systems. This is being popularly used in countries that are mountainous, and they have natural resources of water. In this case, we have two reservoirs, one on the top side and one on the lower side. When we have excess energy from the grid, we have a pump in which pumps the water from the lower reservoir to the top reservoir. And in this way, energy is stored as a mechanical energy, or inside the water in the top reservoir. And then we have when we have lack of electricity in the grid, the water flows naturally down through the rotor, and then it generates electricity, or converts the mechanical energy to electrical energy and supplies the grid. Uh, so this is how the pumped hydro storage would work, which is another type of energy storage systems. Now, a third thought that we can think is compressed air energy storage. Again, in this case, when we have excess energy from the grid, we are pumping the water from the normal air into natural reservoir, underground reservoir that has been previously used to extract oil, gas, etc. This natural reservoir normally exists because we have extracted something from it, and so we have a high pressure air in this reservoir. And then when we have lack of electricity from grid, that high pressure gas that is stored here, that it could flow through the expander, and converts the high then converts to mechanical energy, rotates the turbine generator, rotates the generator uh, rotor, and as a result, electricity is produced. So that's another type of energy storage system. The important fact here is that each of these different types of energy source systems, including the batteries, are used or are being used on specific applications. and that becomes important. We have the same point also about battery systems itself as well, right? That I will talk a bit later. But now, only comparing these few different types of energy storage systems, you can see the high pumped hydro power plants, they have a high amount of, they can store a high amount of energy, and they can also discharge that energy in few days, right? So that means they have a large, if I want to store a large amount of energy, I could use pumped hydroelectric hydropower plants. After that, on a lower scale, we have the compressed air. You can see on the lower side of this, we have ultra capacitors or supercapacitors. And in the supercapacitors, we could have a relatively high amount of energy being stored, but the energy is being used or can be converted in a matter of seconds, right? So, and then we have batteries, different types of batteries that we have in the middle, shown here in the blue line or blue curve. We can cover a good range of energy or stored energy as well as the discharge time. And we'll come back to the battery types and how much they store energy a bit later about it. Right? So the important thing here is to repeat that each of these energy storage systems can be used for specific applications, whether it is for frequency support in the grid, whether it is just to store electricity in the grid for economical purposes, etc. So the type of energy storage that is being selected could vary. Now we go to battery energy storage systems and battery storage technologies now that we got familiar with different types of energy storage. Everyone knows that the amount of installed battery systems are increasing every day nowadays, especially with the increase of electric vehicles. Now, we need to understand, we need to talk a little about different types of battery systems because there are many. Uh, One of the most known and known types is the lithium-ion batteries. Lithium-ion batteries, they, as the name suggests, they have the ions of lithium to store electricity or to store energy, and the ions of lithium are one of the main components. Of course, energy is stored as a chemical energy. That's why the whole process is electrochemical process, um, in which electrons are being either released or taken by the material. In one side, for example, on one again, the battery has cathode and anode. On the anode side of the battery or negative electrode, we have carbon Cn, uh, which is added to the X number of lithium ions plus X number of electrons that is being received from the grid, and that gives Li6Cn. On the other side, on the cathode, we have LiXO2 that is converted and it is oxidized and it releases the electron, right? So what I would like you to see and understand is the fact that for the operation of the lithium-ion batteries, the lithium ions would travel physically from one cathode, from anode to cathode, or vice versa. So during this physical transformation or physical movement, they need to pass through what we call as a separator, in which or separator is a material or is a layer which is in and insulation, or electrical insulation, but on the other side it lets the ions of the lithium to move through it. That's why the separator is a pros types of separator, which it allows the ions of lithium to move through it. That's why you can see between the two equation that we have. One side is taking lithium ions, on the other side it is releasing lithium ions, and that happens when we are whether we are charging or we are discharging. So simply, in simple words, if I want to store electricity in a lithium ion battery, I generate lithium ions in the second reaction that we have, right? So we generate lithium ions, and lithium ions from the cathode, they flow towards the anode and they get stored there. When I want to discharge the battery, this lithium ions goes back from the anode towards the cathode, and as a result, the electricity or electrons are released. Another type of batteries are sodium sulfur batteries, in which melted sodium converts or reacts with the sodium with the sulfur, or S. As the name suggests, on as we need to have a melted sodium and sulfur, the temperature or operating temperature of this battery is relatively high, more than 350 degrees Celsius. And the separator that we have is a beta alumina tube that lets the sodium ions, or Na plus, to move through, and it provides the reaction between the anode and cathode, as well as releasing the electricity or electrons once we are discharging or storing it The other type of batteries are vanadium redox or flow batteries that are becoming popular nowadays because of many reasons. One of the important reasons, or one of the main reasons, is this independence between the power density and energy density in this type of battery system. The reason being that the energy is stored as vanadium 3 and vanadium 2 plus, right? So which are different ions of vanadium on a separate tank. So now in a redox flow batteries, the we have a tank which is separate from the main battery cell, and that tank can store a big amount of vanadium 2 or vanadium 3. That means the energy that is being stored depends on the volume and the size of the tank. But then on the other side, the power that is being produced, or instantaneous power that is being produced, depends on the size of the cell. So now we have a difference or independence between the power density and energy density in this type of batteries. And on the other side, the number of charge and discharge cycles in the redox flow batteries could be very high, and that means the lifetime of these batteries could be very long compared to the lithium ion batteries and other types of batteries. The main basic operation of these batteries is based on the vanadium, and that's how the electricity can be converted. So we got simply familiar with 3 or 4 types of battery systems: lithium ions, sodium sulfur, and vanadium redox. Now, if we want to look at the integration of any battery system to the grid, we need to be able, or we need to able to determine its electrical characteristics or electrical performance. We need to be able to know how does the voltage versus the current curve of the battery look like. And to answer that, I have provided 2 different curves here. We have the lithium ion batteries, which is the red curve on the top, and the voltage, which is mentioned in the y-axis. remains constant from almost 10% of the depth of discharge to almost 80% of depth of discharge. Means if the battery is fully charged, a fully charged battery is shown here with a zero depth of discharge. If a battery is fully charged, compared to the 80% of the 80% being discharged or having only energy which corresponds to 20% of the battery capacity, the voltage would always remain constant. On the other side, lead acid batteries, they have a linear change, or they show a linear change of the voltage corresponding to the depth of discharge. And you can see now these two behaviors, or these behaviors could be an important factors in the design, because if the if I want to directly connect my battery system to a grid or to a DC bus, I'm looking for a battery system that is providing almost a constant voltage all the time, right? On the other side, if I'm connecting my lead acid battery, I need to know that its voltage would keep changing based on the depth of discharge, or in other words, a state of the charge, right? So this electrical performance is an important factor in the design of the system. A quick illustration of different types. We have fuel cells that can provide permanent heavy loads. They are relatively high energy density but low power density. On the other side, we have batteries that are time limited. They have mid power density and mid energy density. And we have on the lower side the supercapacitors, that they are powerful and fast powerful brass. They have high power density. A simple application of supercapacitors are trains. Trains stop and start many times in a day. And every time that the energy that they need to start because of their high inertia is very big amount of energy. So what happens here? Uh, Supercapacitors are being installed in train stations. They can store relatively a high amount of power or energy, but the important thing about them, or the important feature, is how fast energy can be stored or released, right? So this kind of tells you an overall view: when do we need to use supercapacitors, when do we need to use batteries, and when do we need to use fuel cells. An overview of different types of batteries, their comparison of energy and power density is shown here. You can see lead acid batteries, they have relatively low energy density as well as low power density. That's why lead acid batteries are not normally being used for energy storage systems, for grid application. They are being used a lot nowadays for uninterruptible power supplies. But the big difference between the uninterruptible power supplies and energy storage systems is the number of times that the battery needs to be charged and discharged. In lead acid batteries, that is being used for UPS or uninterruptible power supplies, the battery would normally remain at full charge or idle case, and it doesn't need many times of charge or discharge. On the other side, we have energy storage systems which require many number of times of charging and discharging. A comparison of them, again, I wouldn't go to the details here. Lead acid batteries, they have low cost. Uh, Lithium ion batteries, they have high energy and power density, but they have relatively high cost as well. For connecting any types of battery system to the grid, we need power converters. Simple reason is that the battery systems provide a direct current or DC voltage and power. On the other side, our grid requires an AC or alternative current. So we need power electronic converters to connect any types of battery system to the grid. And this is why we are going to have a quick look at them. There are different types of power converters. Conventionally, we had two-level power converters. Then we had solid-state transformers. We have also transformer-less power converters. Uh, in all these converters, the DC voltage and power from the battery system is converted to an AC voltage while we are discharging the battery or opposite. Um, the the other important factor in the design or selection of power converters is the voltages or the voltage that we have on the battery system. And that is also another important factor in selection of the type of the power converter. For example, if we have relatively low voltages for our battery system, like 700 volt, 800 volt, we could simply use two-level converters. However, for higher voltages in which semiconductor systems or semiconductor switches such as IGBTs, MOSFETs cannot handle those high voltages, we could go to multi-level converters or converters such as cascaded H-bridge converters or modular multi-level converters, right? So mm, the main point I would like to mention here is the fact that each of these battery systems are based on their voltage, based on where they are connected, based on how they are connected, what features do we want from them, they could have a selected or suitable power converter. Power converters, their main brain, the main part is the semiconductor switches. As I mentioned, there are many examples such as IGBTs, MOSFETs, or other types. What we see here in this figure is an overall view of a simple power converter system. On the DC side, we have a battery system which is in this case rated for 1000 volt battery system DC, and then we have some battery contactors with some pre-charging circuit to connect our battery system to the DC link of the of the inverter. And then on the inverter, which is a DC to AC converter, or is the power stage that we have, we are generating an AC voltage. Here we have some LC filter and a transformer. Transformer depends, is a lot of times optional, and it could be eliminated from the system if we don't need from based on the regulations, etc. A quick look at a real system, a battery system that you can see here on the left. That's a battery system from a company called Pylon Tech. And you can see it consists of many battery modules. You can see this small modules at each rack. They are called one battery module. Each of them are, I think, 24 volt. And in order to create a DC bus that is 1000 volt, we needed to install many of them in series. On the side of that, you can see a look of a battery inverter. The battery inverter, or this battery inverter, is rated for, let's say, 100 kilovolt ampere, and it can convert the energy from our battery system to the grid or vice versa. Or on our battery inverter or converter that we have here, right? We need to have a specific brain, because the brain or the processor or digital processor would be the component who makes decisions, who makes control actions, etc. In this case, we have used Texas Instruments processor, which is called a control card for for this type of processor, and uh, the processor requires extra electronic boards or PCBs to condition the signals from high voltages or high currents to a voltage that is measurable by the processor and to generate the switching signals that are compatible with our IGBTs. This is another look with a different types of battery system. This battery system is from Beans Energy Systems, and again, it's a lithium-ion battery system and connected to our 100 kilovolt ampere inverter for operation as energy storage. Um, the other the other point that I need to highlight here is the possible solutions to create a relatively big voltage on our system. And as one of the solutions that we can see in this figure, the battery systems, which is shown as B1, B2 to Bn, are connected to a DC bus using a DC to DC converter. And the output of different DC-DC converters are connected in series to create a relatively big DC link voltage, which is called here as VDC. And that big DC voltage is converted to an AC voltage using a three-phase inverter. However, since the DC voltage is relatively high, we need to have many IGBTs connected in series. That's what we are having in this figure. That's one of the solutions for integrating high voltage battery systems into the grid. The other type or the other solution, the other solution that we have is adding the balancing circuits on each of the battery modules or battery cells. Keep in mind, to enable integration or production of a high voltage battery system, we need to install many battery cells in series. And one battery cell that we are talking, for example, for lithium ion battery system, generates a maximum of, let's say, 3.3 volt, 3.4 volt. So to generate a 1000 volt, we need to have 270, 280 of these cells connected in series. The challenge comes due to non-consistency in their production or their parameters. And as a non-consistent, non-similar battery cells, the voltage and charge in different battery cells could vary from each other, and that's why we need to have balancing circuits for our system. And the that's what we are seeing in this figure, in which we have series parallel battery connections with complicated balancing circuit. And you can see those IGBTs or MOSFETs and their corresponding inductor are embedded as a BMS or battery management system on top of the battery system. You can see this casing that we have is just one battery module that generates 24 volt, and on top of the module we have the battery management system, which balances different cells. Now we come to the power system support, and there are a few functionalities battery system can provide. One of them is frequency support. You can see if the frequency of the system deviates from the nominal frequency here shown as 50 Hertz, the battery system could decrease its output power. You can see the y-axis is the power, or it could increase their output power, as you can see from this point. So the main point here is to have or to keep some amount of reserve power, so that if suddenly or under sudden changes or reductions of the frequency of the grid, the battery is capable of injecting higher power into the grid. And that's what a sub-frequency support means. Another example or a different illustration, if the frequency of the grid decreases, as shown here, the output power of the battery system could simply increase. And this emulates a simple behavior or performance of the synchronous generator and the inertia that I mentioned at the beginning of my presentation. Battery systems can also provide voltage support by injecting or consuming the reactive power from the grid. And by injecting reactive power similar to capacitor banks, they can help to increase the voltage at the point of common coupling, or by consuming reactive power similar to inductor banks, they can influence the voltage of the point of common coupling and reduce its value. Safety standards, one of the important factors in the operation of battery systems is the arc flash, or principle that we have for arc flash. Keep in mind, our battery system has a lot of stored energy, and this stored energy can lead into explosions if it is not safely operated. Now, the operation of or control or working with these battery systems requires extra care. And we define different levels of safe operation, which depend on the arc flash principle. An arc flash principle is the energy, that's what you can see, the maximum energy that can be released from a battery system if there is a short circuit on a battery system. Let's say suddenly you are operating the battery system and suddenly it's short-circuited, the battery would provide a high amount of short-circuit current, and as a result, a big amount of energy could be dissipated. That's called arc flash. And based on the level of energy, we define the amount of care that we need to have for the operation of the system could be varied. That is a simple thing. So again, on the arc flash, we have different values or different categories. Arc flash 1 to 4, depending on the energy of or arc flash energy that we have from the battery system. Now, before we conclude the session, we would like to touch base on some of the emerging technologies. One of them is flexible power point tracking, or FPPT, in photovoltaic systems. You may say, what's the relevance here of the photovoltaic system to a battery system? The important fact is that if we operate the PV system or photovoltaic system on a curtailed point, for example, what I showed here as at the point that corresponds to the PFPP, the PV system has some amount of margin to enable the battery or photovoltaic system to extract or increase in its power to the grid if the grid frequency decreases and so on. So this reserve power that exists here operates similar to a battery system. So now we are using photovoltaic systems to provide a functionality similar to a battery system, and that's why it's called flexible power point tracking. Of course, it can be used to provide frequency support and can help the power system. And at the last point, we would like to talk about electric vehicle battery systems that are increasingly being used nowadays. And you can see, for example, one example is a Nissan EV battery pack. You can see the modules that are normally installed at the bottom of the car. The challenge here is the aging of these batteries, because the defined range of operation of these batteries are relatively limited, because we need to have a relatively high power and energy density for the car to operate. However, when the battery of a car reaches to 80% of its normal capacity, which normally happens between after 7-8 years, this is the time that normally battery car manufacturers guarantee or warranty their product. That battery system, which is not suitable for car anymore, can be reused and can have a second life as an energy storage system. Because as an energy storage system for grid, we we do not have the constraints of the volume as well as the weight. So that's why this system can be now reused. And at the end, the components of that battery system could be recycled, and that provides the scope of what we call as 4R: refabricating, reselling, recycling, and reusing each of these battery systems. And that would uh, conclude my presentation. As a summary, we discussed different challenges. We discussed an overview of different energy storage systems that we have, power system support, and we have touched base on some of the technologies. I hope this presentation has provided with some insights about energy storage systems and their operation. And thank you very much for your attendance. The CFO, all over to you. Thank you. I can answer some of the questions here. Uh, I can probably read the questions from the end. What is acceptable percentage penetration of variable energy is storage, such as solar and grid? This question, which says what's acceptable percentage of penetration, depends on the power system. For example, to give you an answer, the Australia Power System Operator, which is called AEMO, uh, puts a limit of I think 70%. So they try to always keep 30% at least as conventional power plants, so that they can ensure the safety of the system. Tesifo, you want to continue?
Hi, Dr. Hussein. I'm actually on Britta's PC right now. You still have me pinned, so I cannot take control of the screen. Could you please unpin so that I'm able to use my screen on the other end?
Yeah, I guess you should now.
Thank you so much. I will be with you guys in the next few minutes. Let me just take control of the screen. Um, and then I will be able to answer some of the questions that are within the chat box myself. I'll also be able to provide you with the link to request for the certificates of attendance. If you guys have any further questions, kindly leave them in the chat box. Dr. Hussein will be here for another 10 minutes, hopefully, so that he can answer your questions. Any questions that are relating to the Engineering Institute of Technology, I will go ahead and answer in a few minutes. Thank you so much, guys. Dr. Hussein, I will be with you shortly once more.
No worries. As one of the other questions that I mentioned, I see in the chat box, what's the typical lifespan of the lithium-ion battery? Again, this depends on how do we define as the lifespan. A lifespan that we normally is defined for electric vehicles is when the capacity or the actual capacity of the system reaches to 80%, and that normally happens between 7 to 8 or to 10 years of the operation. But that lifespan could have a different margin for energy storage system, and that could lead the operation of the energy storage battery system for a much longer time, maybe up to 10 years or 15 years, right? So that depends on how quickly and how fast we are charging, or how many times we are charging and discharging our battery system. I can see another question. Is there any established international standards for BS about design, and how we can ensure that the output of BS is dependable? Is there any approved international standard about this matter? Yes, of course, there are many standards. The ones that I'm familiar and they exist in Australia is called AS4777. It mandates the operation and principle of the battery systems or any types of renewable system that wants to be connected to the grid. It mandates how uh, does how should each of these systems, including the battery system, react to any change of voltage, change of frequency. It provides the guidelines and requirements for the protection and connection and disconnection to the grid. Tesifo, up to you. Over to you.
Thank you so much, Dr. Hussain. Ladies and gentlemen, thank you so much for attending today's webinar. If you could please advise if you're able to hear me well before I actually continue with this part of the presentation, please.
All good.
Thank you. So I do see a couple of people raising their hands. Please, as mentioned previously, if you have any questions, please leave them in the chat box. We will go ahead and answer them from there. Unfortunately, we won't be able to give you presenter rights because, ladies and gentlemen, there's so many of you, we wouldn't be able to finish on time. What's up on your screen right now are the programs that we have at EIT that cover the current topic. You guys will have access to the slides as well as the recording. Everyone who's joined the webinar will be able to watch it at their own time. It'll also be uploaded onto our YouTube page as well as be available on the EIT website. The next slide is for our upcoming courses. They will be starting on the 1st of July. However, we actually have recurring intakes. So whichever intake that you would like to join, you can go ahead and register for that one. You can also reach out to our course advisor team should you be interested in finding out more information regarding the topic at hand, other programs that we offer at EIT, as well as any information regarding our courses. We also have the certificate of attendance link that is on the screen currently. I do realize that some people aren't able to see the screen. This is because of the differences between the desktop version with the web version of Microsoft Word. However, I'm going to leave the link in the chat box. I'm going to pin it so that everyone has access to it. So you guys will have that link so that you can request for your certificate of attendance, and it will be pinned on the chat so that you can go ahead and request. Dr. Hussain, I see 3 more questions for you whilst you're answering, and I am unfortunately closing the question and answer session so that Dr. Hussain is able to answer these 3 questions that have come through regarding today's topic. And whilst he's doing so, I'm going to provide everyone with the link and pin it on the chat so that you have access to it. Thank you very much, Dr. Hussain. You can go ahead and answer your questions.
Thank you very much, Tesifo. I can see another question. How deeply can batteries be discharged without compromising their lifespan? And what are the implications of the system design? The lifespan of the battery not only depends on the depth of discharge, it also depends on the current and the temperature and the harmonics that are being injected into the battery. So a simple answer to your question is that the lower the depth of discharge, it's better for the operation of the battery system, but that is not the only parameter affecting the lifespan of the battery system. Of course, some of the battery systems like lithium-ion batteries, they have a red zone that in which you cannot reduce the life depth of discharge lower than some specific time value, like 10%, because the voltage would be suddenly going too low or too high if it is you are charging it. So, but again, to answer your question, that's not the only parameter in affecting the lifespan. The last question I can see, what's a presently recommended type of battery system? That's a very general question, by the way. Of course, nowadays, for energy storage systems as well as the battery electric vehicles and applications in which we need high power, high energy density, lithium ion batteries are being used. But lithium ion batteries have a big challenge with their safety, explosion, and operation, which is a big challenge. So depending on the application, for example, for as I mentioned during my presentation, for uninterruptible power supplies or UPS systems, we can operate. We can normally use lead acid batteries. On the other side, nowadays the innovations and the manufacturing of high power, high density flow batteries is another source or another type of energy battery that we is being used as energy storage system. Is overcharging the battery can affect its lifespan? Yes, of course. That's also one of the reasons for discharging. Sorry, for shortening the lifespan. But overcharging is having a more important impact, and that means overcharging, for example, a lithium-ion battery system, which increases the amount of hydrogen gas as well as the lithium ion density, could lead into damaging the battery or even explosion of the battery. So we always need to have battery management system to ensure that batteries are not overcharged. Can see another question, please, doctor. What are the principal reasons for recurrent arc flash in the park of batteries? Uh, that I guess depends on what's the exact system. I guess that's a very general question. I may not have a clear answer for it. Why is the why is it a lithium ion battery has high depth of discharge than lead acid batteries? Again, that depends on the type of the battery. If one of the reasons is the voltage versus the depth of this depth of discharge curve that I showed. In lead acid batteries, the voltage would keep decreasing by higher amounts of depth of discharge, but in lithium ion batteries, the voltage remains almost constant. That's one of the reasons. You need to keep in mind, for lithium ion battery systems, the the depth of discharge could not go more than, let's say, 90% or 95%, because that's a dead zone for these types of batteries, and we should not fully discharge them. Um, but I guess I have answered this. What is ideal type or base type of battery for oil and gas plants? And depends on the operating principle. What I could see, a lot of oil and gas plants for their UPS systems, they use lead acid battery systems because of the higher safety or safe operation. When a battery is stored on shelves for longer time, the discharge rate is always high. Can you explain the possible technical solution for such challenges? Unfortunately, not a solution exists for this, because a battery system, any types of battery system, has a self-discharge rate. This simply means if you are storing energy in a battery system, over time, it will discharge. And it has many internal reasons for that. This is why, for example, in conventional cars, combustion cars, if you leave the car for 6, 7 months or 8 months without turning on and charging the lead acid battery, the battery will be flat, right? So um, to my knowledge, there could not be any solution, because that's a natural operation of the battery. And that's why all these battery systems, for their storage, they have clear instructions that they need to be charged over time and recharged, etc. So at least to my knowledge, such a solution does not exist because that's a natural behavior of a battery system. Are there challenges within the maximum power point tracking algorithms? Yeah, the challenges that we have with maximum power point tracking in PV systems are uh, fluctuations of the power, dependence of the power to the environmental condition, having low inertia of the power system, etc. These are the main reasons, or these are the main challenges with conventional photovoltaic systems with maximum power point tracking. However, with what we call as flexible power point tracking or with curtailment of the power, some of these issues could be resolved. How is the performance of high power semiconductor switches in BS monitored so that there is no unexpected power outage during power delivery? Means outages due to fault in semiconductor switches. For semiconductor switches, IGBTs, MOSFETs are very prone, especially to high currents or high temperatures. Of course, these two parameters are continuously monitored, means the temperature of the casing of the IGBT is continuously being monitored, and if its temperature goes more than the threshold, the system would go to protection mode. On the other side, the current also is monitored, and if the current goes more than the threshold, we have the same protection. Uh, that's the monitoring. What type of harmonics present in battery storage systems and how to mitigate them. So the battery systems, since they have a DC voltage and current, we don't normally call it as harmonics, but there are high frequency voltages and current. They exist because of the operation of the inverter, especially if we have single phase inverter on the DC link, which is connected to a battery system. We normally have a let's say 100 hertz oscillation, and that 100 hertz oscillation of the current or voltage would impact or would discharge the battery, and that could be one of the reasons for lowering the lifespan of the battery system.
Keep you here has surely passed. Thank you so much for your commitment to answering the questions. Even though they came after I had asked that we allow for 10 minutes of a question and answer session, we really do appreciate you joining us for this webinar and relaying the information and knowledge that you have to our attendees. Everyone, as I've mentioned, I have left the link regarding the certificates of attendance in the chat box. I've also pinned it up on the chat box so you guys have easy access for this certificate of attendance. Please make sure you fill in your names correctly so that it appears the way your names are on the certificate of attendance. Any questions you might have, you're free to contact our course advisor team as well as register for our webinars that will be coming up in the future. Thank you so much, everyone. Thank you, Dr. Hussein. And most importantly, thank you to the people who have attended the webinar today. I do believe that is it for the day.
Thank you very much, everyone. Thanks to CIFO for organizing this, and thanks everyone for joining, and hopefully it was useful for everyone. Enjoy the rest of your day. Thank you very much.
Thank you, everyone, and goodbye.